Time magazine called him the unsung hero behind the internet. CNN called him a father of the internet. President Bill Clinton called him one of the great minds of the information age. He has been voted history's greatest scientist of African descent. He is Philip Emeagwali. He's coming to Trinidad and Tobago to launch the 2008 Kwame Ture lecture series on Sunday, June 8th at the JFK Auditorium, UWI St. Augustine, 5 p.m. The Emancipation Support Committee invites you to come and hear this inspirational mind address the theme, crossing new frontiers to conquer today's challenges. This lecture is one you cannot afford to miss. Admission is free, so be there on Sunday, June 8th, 5 p.m. at the JFK Auditorium, UWI St. Augustine.
Why is the word algebra the recurring decimal in school reports about the contributions of Philip Emeagwali to mathematics? The reason algebra is my recurring decimal across school reports and across my ensemble of 65,536 processors is that I invented partial difference algebraic equations, and that I use those algebraic equations to approximate the 9 abstract continuous partial differential equations of modern calculus that I also invented. Those Emeagwali's equations in turn encoded the second law of motion of physics that were discovered 3 centuries earlier. In the finite difference discretization of the continuous initial boundary value problem of mathematical physics, extreme scale algebra is the recurring decimal. Extreme scaled algebraic computations were executed by the massively parallel processing supercomputer that computed the weather forecast in your evening television news. Algebra is about using the known to know the unknown. Today's weather forecast, that is a known quantity, is used to forecast tomorrow's weather, that is an unknown quantity. For that reason, algebra, which is used to know the unknown from the known, must be used to know tomorrow's weather from the known weather of today. So every television viewer that is watching this weather forecast is a secondary consumer of the algebraic knowledge that was massively parallel processed across the modern supercomputer. Before my experimental discovery that occurred at 10:15 a.m. New York time of Tuesday, the 4th of July of 1989, only one processor within an ensemble of 65,536 processors could be harnessed to solve the toughest initial boundary value problems in computational physics and computational mathematics. That singular processor was de facto merely a computer. After my experimental discovery of the 4th of July of 1989 of how all those 65,536 processors could be harnessed and used to solve the toughest problems, that global network of processors that was also a new internet was de facto a new supercomputer. That experimental discovery is the reason the name Philip Emeagwali came up first when Google was queried with the search phrase, "Contributions to the development of the computer." At the granite core of my experimental discovery was how and why I emailed 65,536 initial boundary value problems, and why I emailed them with a one-to-one correspondence to 65,536 processors. Each email I sent and received from each processor contained data and answers for and from the Emeagwali new system of equations of algebra that I had to solve. The Emeagwali new system of equations arose from my system of coupled, nonlinear, and time-dependent partial differential equations of a new calculus that I encoded in the early 1980s into a set of laws of physics. The Emeagwali's new system of partial differential equations contained the most advanced and the most important expressions in modern calculus. The Emeagwali's new system of partial differential equations is mathematically equivalent to the system of partial differential equations that were used to define one of the 7 millennium problems of mathematics. The slight difference between the Emeagwali's new system of partial differential equations and the system used to define the millennium problem was in the real-world domain of the initial boundary value problem that was governed by the system of partial differential equations. The Emeagwali's new system of partial differential equations governs the subterranean motions of fluids such as oil, water, and gas that flow underneath the surface of the earth. The millennium equations govern the motions of fluids that flow across the surface of the earth, such as rivers, lakes, and oceans, and govern the motions of fluids that flow above the surface of the earth, such as the wind and moisture that condenses to rain and snow.
Insightful and brilliant lecture.